This presentation, we'll start talking about truth trees, and we're going to spend quite a bit of time on truth trees. Truth trees represent one of the uh, fundamental ways in which we can prove whether or not a logical sequence is valid or invalid. So, if you remember from our introductory presentation or video, I talked about how in this course we're going to be focusing mainly on the structure of arguments and determining whether or not they are valid or invalid. In this sort of section of the course, we're going to do that by using truth trees. In the next section of the course, we'll do proofs. But right now, we'll just focus on truth trees. And truth trees are unique because they give us a ability to diagnose a sequence, determine whether or not it's valid or invalid, and then if it is invalid, we can identify truth values for each of the different propositions that are included in the truth tree and say, hey, here's a counterexample where if this letter is true, this letter is true, this letter is false, then it's invalid, and we know that this whole sequence is invalid. We'll get to more of that once we progress further on, but we are going to take this rather slow. In this presentation, I'm just going to give you an overview of truth trees. There's going to be a lot of information here, so you might want to watch this presentation a couple times over. I'm going to do, first, I'm going to give you an account of what makes each of the operators either true or false. So I'm going to give you an oral representation of what makes them true or false. And then I want to explain the anatomy of the truth trees so you can see which side goes for which side, because then we're going to see what the actual rules for the operators are in the truth tree setup. We're going to use the rules that I give you here in the first part, just orally, to build the truth tree rules that we'll use when we're actually performing the truth trees. And then I'm going to round it out with a couple of practice problems. So first, let's start with what makes each operator true or false. So let's start with just the ampersand and the wedge. The next slide we'll do the conditional, the arrow, and the tilde. And then the slide after that we'll do the biconditional, but let's just do these one at a time. So I use the Greek letters phi and psi. So if you're not familiar, this one is phi, this one is psi. When we're giving these definitions, we're giving just an abstract explanation for what makes the operator true or false. Really what we're focusing on is this thing right here. We use these Greek letters because we don't care what's standing in on the left side or right side of it. The rule will apply no matter what. We could say that the same rule will apply if this is P and Q, or R and T, or S and L. So the same rule will always apply. And the reason why we use meta variables, these Greek letters, the phi and psi, is because what we're focused on when we're applying these truth rules is the operator itself. And so what we'll be focusing on is identifying main operators, but this rule will apply for something that looks something like this. Yes. Because the main operator will still be the ampersand. Same thing applies in this one. Let's go with R. Or we can do R and P, Q, or we could do, let's say R and P or Q, arrow L. And you might be thinking right now, wow, this all looks very strange and unfamiliar. That's fine. We're going to build up to some of these more complicated ones. All I'm trying to show you right now is that the main operator is the ampersand. And what these meta variables stand in for is the left side and the right side. So we could treat this as a psi, we could treat this as a phi. The same rules will apply when we're saying which side is true, which side is false. But through examples that might become a little bit clearer, but that's why we use the meta variables, because anything can stand in for them, even something as long and complicated as this. So what we're focused on with giving these rules is the operator itself. So let's look at the rule itself for the ampersand. Let me get rid of stuff so it's not in the way. So what makes an ampersand true? An ampersand is true if the phi is true, so if the left side is true, and the right side is true. I'm going to give you an example that makes this pretty clear as to why this is the case. So say if I have, or say that I want to make the statement, I have pennies and quarters in my pocket right now. I want to say that I have both pennies and quarters. Well, what makes that a true statement? Well, it makes it a true statement if I do have pennies in my pocket and I do have quarters in my pocket. If I have pennies but I don't have quarters, or I have quarters and I don't have pennies, and I say I have pennies and quarters, then I'm not telling the truth, which gives us the false version of this operator. So this statement saying I have pennies and quarters in my pocket is true if I have both pennies in my pocket and quarters in my pocket, which would mean these two things are true. It would be true to say that I have pennies in my pocket and true to say that I have quarters in my pocket. But what would make it false is if I said I have pennies in my pocket and quarters in my pocket, when really all I have is quarters or just pennies. Actually, I'll go with the first example. So I'm going to use green for true and red for false throughout here. I think it makes more sense, or at least it can make more sense. So say if it's true that I have pennies in my pocket and it's false that I have quarters in my pocket, and I make the statement, I have pennies and quarters in my pocket, it's obviously false because I'm missing one of them. It's false that I have quarters. That's what this statement is saying. So what makes the ampersand true is if both sides are true. What makes an ampersand false is if one side or the other is false. So as long as one side of an ampersand is false, it is false. But if both sides are true, then it's true. I'm going to get rid of that ampersand and put in the black one to hopefully stay consistent with this green equals true, red equals false. So both of these will be false statements. And this one up here is true. So just remember that for an ampersand, both sides have to be true to make it a true statement. If one side is false, then it's false. And remember, what we're talking about is this statement in particular. So now let's move on to the wedge. So the wedge is true as long as one of the sides are true. As long as either left side or right side is true. So let's use the same example as before. Say I want to say I have pennies or quarters in my pocket. I say I've got either pennies or quarters in my pocket. Well, let's just say that it's true that I have pennies, but it's false that I have quarters. Well, that's still a true statement because I'm saying I have one or the other. say if I have, or I don't have pennies, and I do have quarters. That is also a true statement. Because my statement, what I'm representing here is saying, I have pennies or I have quarters. That's what this is saying. Left side's pennies, right side's quarters. And these statements, these renderings, are what makes the sentence true. It's true that I have pennies, but it's false that I have quarters. But the statement, I have either pennies or quarters, is still true. Now just the opposite. If I have, or say I don't have pennies, but I do have quarters in my pocket, saying this line or this sentence that I have either pennies or quarters is true because I do have quarters. I might not have the pennies, but I do have the quarters, but that's enough to satisfy the truth conditions for this sentence to make it true. Now, what makes it false is the both of them being false. So, if it is the case that I don't have pennies and I don't have quarters in my pocket, then this statement, I have either pennies or quarters in my pocket, is false. That seems, implicitly true. Or, sorry, seems obviously the case. Let's just put it that way. I got to make sure that I'm not too loose with the terms true and false here. So if I said I have pennies or quarters, and the red just says I don't have either of them, then that's a false statement. That's what we're getting at here. Now, you might be wondering, what if I have both of them? What if I have both pennies and quarters? I see all the other options up there, but I don't see this option. In this situation, we have to ask, are we doing the inclusive or an exclusive or? I'm not going to go into all of that because it just complicates things unnecessarily. Some of this stuff is going to be really complicated because it's just going to be something you're unfamiliar with. And it's going to take some practice. Again, some of the things that we talk about in this class are, I understand, unfamiliar territory, but hopefully the more that we do it, the more it'll make sense. So I'm going to avoid the whole inclusive, exclusive, or conversation with you and just tell you that if both of them are true, it is true. Saying I have either pennies or quarters in my pocket, and it being the case I have both of them, that's still true. I have either pennies or quarters. I actually have both of them, but the statement either or is still true because I satisfy the conditions for either of those disjuncts, for either side of it. Now, if we go back up here, I should have probably said this one too for the ampersand. But say if P and Q are both false, then obviously it is false. So all three instances of those are false. Only this one is false down here. Which is another trick that you can use to memorize these rules. You're going to have to memorize them, or at least have them, understand them enough to be able to use them when you go to do the exam. In the case of an ampersand, it's only true where both of them are true, which we see up here. And when we do a wedge, the only instance in which a wedge is false is if they're both false, which we see down here. So those are the first two rules. Let's go on to the next two rules. Now we're going to look at the conditional, the arrow. And again, we're going to use our meta variables because anything can stand in for them. So the conditional is a little interesting to say the least, and probably the best way of explaining why these truth rules work the way that they do is by just looking at the false instance. But let's go through the true instance first. So this statement this arrow, the arrow is true when either the left side is true or the right, or sorry, take that back, where either the left side is false or the right side is true. So let's visually represent this again. So say if we have phi, actually I'll use p's and q's again. Let's say I have a p and it's false, and an arrow, and a q that is true. So I have a left side that's false and a right side that's true. That is true because it matches our truth rule, wherever the left side is false or the right side is true. Now let's look at the case in which both of them are false, where both P and Q are false. Well, looking at our truth rule, it only has to be one or the other. Either the left side's false or the right side's true. The left side is false, the P is false, so it's got to be true. So if the left side is false, then it's automatically true. The same is the case if the right side is true and the left side is true. Even though we're not meeting the phi condition for the truth rule, we're meeting the psi condition for the truth rule. Namely, we are seeing that the Q is true. So that makes the statement true. So in each of those instances, the statement, or the conditional statement will be true. The only instance in which it's not true is where the left side is true and the left side is false. Or sorry, the right side is false. That is the only instance in which it's false. And it's hard to give you an example to explain why the truth rules are this way, especially for these two. Because you might think that, well, if I made a conditional statement and the left side's false, then how in the world can the right side be, or how can it be a true statement if the condition itself is false? So say if I were to give you one of my classic conditional sentences, like, if it rains, I'll take my umbrella. And it's not raining. Well, that statement is going to be true no matter what, because the left side is false. Because let's say this is it's raining, is false. Me telling you, if it rains, I'll take my umbrella, and it's not raining, means that sentence is automatically true. And that's why it's a little bit confusing to try to understand what makes a conditional, try to understand the conditional truth rules using examples. So I want to stay away from doing that. Instead, I want to look at the false case, where it's actually false, where P equals true and Q equals false. Why is that false? Well, let's think of a sentence. I'm going to go back to my tried and true, if it rains, I'll take my umbrella. Say it's true that it's raining, but I don't take my umbrella. Didn't I lie? I told you if it rains, I'll take my umbrella. It's raining, but I didn't take my umbrella. So obviously I'm lying. I lied to you when I said this. This side represents if it rains. And actually, make sure I don't do anything confusing here. Get rid of the red, because now we're just talking about the sentence itself. So if it rains, I'll take my umbrella. I'll just draw a picture. Of course, the picture's not going to look very good either. Sorry. That's my umbrella. Draw little raindrops. So say that's the sentence that we're trying to represent here, and we're trying to determine whether or not it's true or false that if it rains, I'll take my umbrella. And then we start looking at the actual conditions that are happening in the real world. It is raining, but I didn't take my umbrella. So the sentence up here saying, if it rains, I'll take my umbrella is a lie. It's false. It's not true. Because the condition was met, but the consequent is not fulfilled by the condition itself. So if it rains, I'll take my umbrella is true as long as it's either not raining, or if it is raining, I end up taking my umbrella. But it's false if it is raining and I didn't take my umbrella. That's what we're trying to get at here with the conditional. I know it's a little screwy. Sometimes it's just best to memorize these rules in logic. I can give you examples, but sometimes they don't obviously click. So my recommendation is to try to memorize these rules, go through these practice problems, and again, always feel free to contact me when something doesn't make sense. But let's go through the next one. Let's go through the negation. So the negation is true wherever the phi is false. And it's going to be false wherever the phi is true. So let's just use the same example that we did before and say, but let's just reduce it down to saying that I possess pennies of some sort. So the sentence, I don't have any pennies, is true as long as I don't have pennies. If I do have pennies in my pocket, then that's obviously false. Sorry. So this sentence here is saying I don't have pennies. What makes that a true sentence? That makes it a true sentence if I don't have any pennies. But it makes it a false sentence if I do have pennies. Saying I don't have pennies and then me happening to have pennies in my pocket makes me a liar. It's false. It's wrong, or it's doesn't follow the rules. So a negation is just saying, hey, not this thing, not this condition, or not this state of affairs. Sorry, should get B. That's all negation is saying. And when we say something's not the case, then it's false for it to be the case. That's what we're getting at with the uh, uh, truth rules here, saying that if the P is false in red, that's saying the state of affairs right now is such that I don't have pennies. And so that's true if I make this sentence. That makes it true. But if I happen to have pennies in my pocket and I say I don't have pennies, then it's false. Red suggests that I don't have whatever, and the green suggests I do have whatever. Or it is the case, and the red suggests it's not the case. All right? So let's move on to the final operator. Let's finish by looking at the biconditional rules. So phi, if and only if psi. And these rules are going to be a little bit unique because, as you'll see here on the first example, what makes this statement true, phi, if and only if psi, is whether both sides are true or both sides are false. So it's true where we say this, so both sides, or where both sides are false. Again, I can give you a detailed description as to why it's the case. It goes to the point because what a biconditional really is saying this, which is why biconditionals are really not necessary in logic, but we're supposed to teach them anyway, so I do. But that's what a biconditional really is. And if you look at the truth rules for the arrow, the only way in which we can make this statement true is by having these conditions hold, where either both sides are true or both sides are false. So, but again, I'm not going to go into a detailed description about that unless you really want it. Let me know. I can let you know. But it's best to just understand that the rule is if both of them are true, it's true. If both of them are false, it's true. So if they match, it's true. So, of course, the opposite version of this is if they don't match. If one of them is true and the other one is false, then the statement is false. So the best way, again, to understand what makes these true or false is, you know, they're true if they match, they're false if they don't match. It's the best way of understanding a biconditional. Again, I don't know if I can give you an example that would make that crystal clear as to why these are the logical rules for it, but I could sort of give you I could give you the logical explanation for it. But besides that, I would just recommend memorizing these rules. So this one plus the 4 before, and just being able to understand when when these statements that we're looking to determine whether or not they're true or false. So this is what we're trying to determine, which is true or if it's true or false. And so then we're looking for when it is true and when that sentence is false. And you'll see why we do this before getting into truth trees, because we need to know these rules to do the truth trees. Now, the nice thing about truth trees is you're not going to have to memorize these specifics in such a very abstract way. When you start to apply them in the truth trees, it might start to make a lot more sense, and when you get to visualize it. And again, when it comes to logic, everything is just about following a rule. If you have if you have an instance of something, you ask yourself, what's the rule? Okay, do that, and then everything else follows from it. The interesting thing about logic, or why logic is something that's taught or something that is even researched, is because all computer operating systems are run on some sort of logic, and they just follow rules. When you put this input, you get this output, and they follow a set of true and false rules, and they're based on the operators that you give them. So that's sort of the application of this, but it's also supposed to give you hopefully a little bit of ease, or at least ease some of your worries you might have right now when you're like, what the hell is going on right now? Why am I seeing P's and Q's and T's and F's? But the point is that everything follows from a specific rule, and as long as you can memorize the rules and apply them, then you'll be in good shape. Everything else follows from it. It doesn't require too much more critical thinking beyond that. Identify what's the main operator, and then use the rule that's associated with that main operator. Before we get into the truth tables specifically, though, I just want to give you the anatomy of truth tables and explain what they are used for. Of course, I think I finished the slide previously saying truth tables, and we aren't doing truth tables, we are doing truth trees. So that's me remedying that mistake from the previous slide. I want to go through the anatomy of truth trees, not truth tables. We're not doing truth tables. Truth tables are another variety of doing what we're doing here with truth trees. Truth trees, I think, are infinitely easier than truth tables. and truth trees are a lot less messier. So we're going to do truth trees. I want to explain the basics of truth trees, though, and how we use them, and how, or what's their worth, and sort of just diagnose the difference or the different aspects of it. So I'm going to give you an example, and we'll see this on one of the next slides when we go through the actual rules for them. So don't feel like you have to understand what's going on this slide. I'll break down the rest, but it's best to give you a diagnosis of what a truth tree is by doing a practice example. So a truth tree, we use these on logical sequences. So say I have this logical sequence. It's saying I have these two things. Oops, a little bit too far. These two things are premises, which means we're given these at the beginning as something that is true. We're told that these two sentences, P arrow Q and P by itself, are true. And we're told that that results, I'm going to try to use a color that's not green or red. This is saying, therefore, or it results in this thing. And so we get these premises, and we're trying to reach this conclusion. And we want to prove it, and we're going to use our truth tree to try to prove it, either that it is valid or invalid. But we'll wait till the very end to sort of discuss that. I just want to work through the rules and show you how this thing sort of is arranged or structured, how the truth trees themselves are structured. But whenever you see these sequences, this is how we'll operate in this class. You'll get a logical sequence that has premises that can range from 1 to however many that I give you. In this class, I probably won't ever give you more than 3 or 4 because we don't do anything too complicated in here. But you can have an infinite number of premises, but you can only have one conclusion. And that's what we're trying to prove. Is that conclusion, or does that conclusion follow from the premises that are given to you? So, how we set up these truth trees, I want to erase this stuff just because I have a lot of room, is we start with a line. And it's best to start it in the middle of the page. Sorry, I tried to make that a little bit thicker. Let's see if I can just do that. All right. So we start with a line, and then we want to put our parts of our sequence on this line accordingly. So we put the premises on the left-hand side, and the left-hand side is representing true. Sorry, changed it to marker on accident. So the left side is saying these things are true. These statements are true. And the left side, we put our conclusion to start, and that's saying that it's false. I usually put in a line because this is our sequence. We have our premise here, we have this premise here, we have our conclusion here. Every single truth tree starts off the exact same way. Premises go on the left, conclusion goes on the right. And what the truth tree is set up is that the left side is true and the right side says false. So if it's on the left-hand side, we're saying this statement is true. If it's on the right side, we're saying this statement is false. So I'm going to go ahead, and I'm going to use the rules that I know. Again, we'll get to this on the next slide. So the only operator that I have that I need to operate on or use my truth tree rules on is this P arrow Q. We'll see that when you have a P arrow Q, you put the you split it apart, and then the left side is false, right side is true. I'll explain this again once we get to a little bit further. I just want to show you what we're doing here with the truth tree. So again, green, true, green's on the left, red's on the right. So when I split them, I have the red P here, I have a green Q here, because the Q's on the left and the P is on the right. So remember, left side is true, right side is false. So what I can use this truth tree for is to determine whether or not it is a valid sequence. And if you remember, valid is just saying, does the conclusion necessarily follow from the premises? We can use the truth tree to determine this by going back up through the truth tree and looking for contradictions. A contradiction is where I find that the same thing is on the left and on the right side of a branch. And you travel back up through to the top. So let's start here. So I'm starting here on this left side where this red P is at. And I'm going to look. I have a red P, so I have a P on the right. And then I'm going to look back through. I got a red Q. That doesn't help me. But I do have a green P on the left. That's a contradiction. What this branch is saying is that P is true and P is false. That can't be the case. Something can't be both true and false. So, what we do when we find a contradiction, when we find something that's both on the left side and the right side, we put an X there, saying that we closed off the branch. When we look at the other side, now let's go over here. I have a Q that's on the left. Let's travel back up through this branch and look, I have a Q that's on the right. So because I have a Q that's on the right here, and I have a Q that's on the left here, I can close this branch. I close these branches, and because there are no open branches, this is a valid sequence. Because both of these branches, actually I'm going to change colors, both of these branches close off. We have X's at the bottom of them. Now, when a sequence is valid, there's nothing more for us to do. It just says that the conclusion necessarily follows from the premises. Now let me change one of these premises and the conclusion. So we're going to change where these are. I'm going to make this Q. I'm going to make this one P. So now our premises are P arrow Q and Q. So I want to put a Q on the left and a P on the right. I'm going to erase those two. So, same thing as before. When I'm constructing this truth tree, I'm looking at the premises go on the left, conclusion goes on the right. It's the same thing every time to start. We're saying that the premises are true and the conclusion is false. So from this, I'll just use my rules again, and I know what they are, and they're going to look the exact same as previously. Either P is false, so either this P is false, and what we're doing is we're breaking down this operator right here. So either the P is false or the Q is true. Again, that's not of interest to us right now. I just wanted to show you where I'm getting this from. So now let's do the same thing we did before when we're saying, hey, does the same thing appear on both the right side and the left side? Let's start with the red P that's down here again. I've got a P on the right, I've got a P on the right, and I've got a Q on the left. I don't have anything that contradicts. I don't have a Q on the left and a Q on the right. I don't have a P on the right and a P on the left. I only have P's on the right and Q's on the left. So what we do to signify it's open is put a circle below it. And that says this branch doesn't close off. There are no contradictions. And then we want to look at the other side. And we say, well, look, I've got a Q on the left, I've got a P on the right, I've got a Q on the left. Here again, we don't have Q's that cancel out, and we don't have P's that cancel out. So we just have an open branch. So this sequence, P arrow Q, Q, therefore P, is invalid because I have open branches. Because both of these are open. They don't close off, we don't put X's below them. Now when we have an invalid sequence, we want to give a counterexample. To say, hey, the sequence is invalid because the values of the propositions are these. You know, if the P is this and the Q is this, then the conclusion can't follow, or it doesn't necessarily follow. So what we do to find a counterexample is we trace one of these branches back through and look for what the values of the letters are. We have a P that is false because it's on the right. We also have another P that's up here that's false because it's on the right. And we have a Q that's on the right, or Q that's on the left that's true. So if we wanted to build a counterexample for this, we would say this is invalid where P is false because it's red. Change this to red to try to stay consistent. And then where Q is true. And how did we do that? Well, we just traced back up through our truth tree and saw P is on the right, P is on the right here, Q is on the left up here, and it doesn't close off, so I can say wherever P is false and Q is true. That's why it's invalid. Now, there will be instances. Here, it doesn't really matter. We could have looked at either side of the branches. We could have followed this other open branch on the right side, and we would have got the same exact values. P is false and Q is true. But sometimes you'll have multiple branches that don't close off, and the values of these letters will be different. And you could use that as a counterexample. There will be instances in which every branch except for one closes off. That is still a counterexample. So say if I had, I'm going to just sketch what a tree might look like. Say I have a tree that looks something like this. And I have this one close off, 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 and this one's open. It's still invalid because I have an open branch. And I would look back through this branch and see what the letter or what the values of the letters are, like I did here. And I would write that as my counterexample. It only takes one instance of a branch being open for the tree to be invalid, or I guess the sequence to be invalid. Again, when we start doing more practice problems and we go through them, hopefully the repetition will make it make more sense. But I'm just trying to give you a diagnosis of what truth trees are and what we use them for. We use them for determining the validity of a sequence. We take these sequences and we want to know whether or not they're valid or invalid. And then we use the rules that we'll get here in the next few slides to determine whether or not they are indeed valid or invalid. And we do that by trying to find contradictions in the different branches of the tree. We try to find those contradictions. If they're there, we close off the branch. If they're not there, then we leave it open and we know that our sequence is going to be invalid. So I want to move on to the rules themselves and just take it one at a time. And then after that, I'm going to give you just a couple of practice problems here. And then what I'm going to do is after this presentation, there will be a bunch more practice problems. That's all we're going to do for the next handful of weeks, is just practice truth tree problems. So the best thing to do is just practice these things as much as you can. I'll keep giving you examples, especially through these lectures. If you need more help with them, always feel free to contact me. But with that being said, let's just move on to the exact truth tree rules for each of these operators. On this slide, you're going to see just a picture from the Pospecial textbook that I typically use for this course. Again, you don't have to purchase it, but it is recommended. It just gives you the rules. And so I wanted to give you the basic overview of all the rules for the truth tree for the different operators. We're going to go through each one specifically on each of the next 5 slides, but this is a good reference point. It's good to put in a notebook or make sure you have it handy as just a good quick cheat sheet when you say, I can't remember exactly what this is. You should try to commit these to memory as best you can. As you'll sort of see with the next few slides, I'll explain that left side here is when it's true. That's not very easy to see. I'm just going to put it over here. So the left sides here are where we're saying that it's true. And on the right sides here, we're saying that it's false. Following from the same thing we sort of mentioned on the other page. But as I go through them, it will probably make a little bit more sense. But again, if you got a notebook, I highly recommend just copying down this cheat sheet because it's going to help you out. So before we go through sequences, I want to show you what to do with the operators themselves on the truth tree when you encounter them. So we're going to look just specifically at how we exercise the rules on the operators whenever we find them in the truth tree. So we'll put the sequences behind us for right now and just look specifically at the rules. Now we want to think back to the previous slides where I gave you the truth rules for the different operators and what the truth values are for what makes them true or false. So we're going to start with the negation because that's where Pospecial started on the previous slide with that handout, and it's the easiest one. So remember, left side means true, right side means false. If you encounter a tilde p on the left side, ask yourself where or what makes tilde p true. Well, if you remember from our previous discussion, what makes tilde p true is wherever p is false. That's what makes the tilde p true. So whenever you come across a tilde on the left side, you just flip it over the line and get rid of the tilde. Now, suppose that you come across it on the right side. Again, right side is false, left side is true. So what makes a tilde p false? Well, what makes a tilde p false is wherever P is true. So same thing as before, we are flipping the letter over the line and we're dropping the tilde. So whenever you come across a tilde on either side of a truth tree, you can remove that tilde by flipping it across the line and getting rid of it. That's all you have to do. That's what makes the tilde rule probably the easiest one in the truth tree. Now let's look at the ampersand. So say we have P and Q on the left side. Left side's true, right side's false. I'm going to keep saying it so that it sort of sticks in your brain. So think back to what our truth rules were for an ampersand. What makes an ampersand true? Well, it's only true where the left side is true, namely the P, and the right side is true, namely the Q. So what makes this P and Q a true statement is that the left side is true and the right side is true. So when we encounter an ampersand on the left side of our truth tree, and it's the main operator, we're just going to break it down into its two pieces, and we're going to put them vertically underneath of it on the left side, because that's what makes it true. Now, if we encounter an ampersand on the right side, what this is saying is that this statement is false. And then we think back to our rules. When is an ampersand false? And I told you before, it's in any instance in which either the left side is false or the right side is false. Now, the reason why I emphasize the and the or on those slides is because that's going to tell you what you're going to do in the truth tree. Whenever you see an and, you're going to stack. Whenever you see an or, you're going to split. You're going to split the tree into two. So what did I just say? I said a P and a Q. This statement, when it's false because either the P is false or the Q is false. So it's going to be either when the P is false or the Q is false. So when we encounter an ampersand on the right side, and it's the main operator, we're going to split the tree, and we're going to put the left side over here, and we're going to put it on the right side because it's false, and we're going to take the right side here, and we're going to split it over here into its own branch, and we're going to put it on the right side also because this is also false. So remember, left sides are falses, right sides are trues. Same thing applies even once you start breaking branches apart. Right side's always false, left side's always true. So for these ampersands, just remember that if it's on the left side, it's when both of them are true and you stack. Wherever P and Q are true, that's what makes that statement true. So they stack and they stay linear. If the ampersand is on the right side, it's saying this is a false statement, and what makes the ampersand false is if either side is false. So we split the tree and we put each side of the ampersand on the right side of the split tree paths. Now, I do want to make sure that we talk about how these things operate with more complex sentences. So I'm going to show you these same rules, just using a little bit different of a statement here using the ampersand. So, say instead of just a simple P and Q, I had a P or Q with parentheses and let's say L or L, if L, then T. And let's say that that's on the left side of my branch. Now, what's important when we're doing logic is to identify the main operator. That's why we have the parentheses. And here, this is telling us the main operator is the ampersand. It's operating on this and this. So what we're going to be focusing on is the ampersand. And the same thing applies as before. When you have an ampersand that's the main operator, it's saying that it is true. These back over so they're in line. So left side's true, right side's false. I'll get rid of this for right now. So we're saying that this ampersand, this statement right here, is true. It's on the left side of our tree. What makes it true? If the left side and the right side are both true. So what we will do is we will put both sides like this. So this is why we used the meta variables before when we were explaining how or what the truth rules were for things, because the main operator is the ampersand in this statement. So that's telling us what we're going to do or which rules we can exercise on the statement. And so what makes this ampersand true is if both sides are true. This is the left side, this is the right side. Once we start moving further down the truth tree, then we have to start using the rules for those specific operators, but that's something we'll deal with a little bit later. So that's how we would write it if it was on the left side. Now, let's just say that I were to write it on the other side. This. Now, shorten this line. Same thing applies as before. So now that it's on the right side, we're saying, well, this statement's false. The main operator is still the ampersand. I have a left side and I have a right side. And what makes an ampersand false is that either one of the sides is false. So we'll take the P or Q, put it here, and we'll put the L arrow T here. Again, we are just looking at the specific sides of the ampersand. We take what's there and we transcribe it into the same spot in the same locale as before. True's on the left, false is on the right. What makes an ampersand false is that one of those sides is false. And so that's what we're showing when we split the branch. Either P or Q is false or L arrow T is false, one or the other. That's what we're doing. So that's the ampersand. Let's move on to the next one. Now let's do the wedge. So, starting with what we did before, let's say we have P or Q. Left side is true, right side is false. We're saying this statement is true. And now let's think back to what our rules were. A wedge is true when either the left side is true or the right side is true. So again, the code word that tells you if you're splitting a branch or not is either and or. You don't split if you hear and, you do split if you hear an or. And so I just said what makes a wedge true is either the left side is true or the right side is true. So we're going to split, because I said either, we're going to put the P on the left and the Q on the left. That's the left, it's the true side, this is the false side. Same thing applies as you start breaking down the branches. So, get rid of those just so that it's not as confusing. That's the rule if the wedge is on the left side of the tree. If you encounter a wedge on the right side of the tree, where it's false, think back to what our rule was there. The instance in which the statement P or Q is false is wherever P and Q are false, where both sides of the disjunction are false. So we will put our P here and our Q here. Again, thinking back to the sentences that I gave you previously when we were doing the truth rules, what makes a wedge true is wherever or whenever one side or the other is true, which we see here on the left side of the screen. What makes it false is where both of them are false. Now let's do another example again, just because I want to make sure that you're understanding how these meta variables things work from the previous slides. And so you know what's going on in the future. So say if I had P and Q or T. What makes this true is still, or sorry, let me back up. We first need to identify our main operator. The operator that's not inside any parentheses, it's outside of everything, is the wedge. So we know that's the main operator. And then that also signifies to us that we have our left side is here, our right side is here. And then we still use the rules in the same way we did previously. What makes it a true statement? What makes P and Q or T a true statement? Well, it's wherever the left side is true or the right side is true. So we would put the P and Q here and the T here. Same thing as before. Remember that all we're doing is one operator at a time. Once we move on beyond this stage, then the next thing we would look at is this ampersand. And, since we did it on the previous slide, let's just go ahead and do it. What makes a P and Q true? A P and Q is true wherever P and Q are both true. So right there, that would be fulfilling this whole part of the tree, going from this starting point. But I just want you to recognize that what we're doing is we're breaking up this based on its main operator. Whenever I'm talking about main operator, it's the thing that's operating on the majority, or actually on all the letters at the same time. So breaking up this main operator, we get to this point here. P and Q on the left, T on the left as well in a broken path. Now if we put the same thing here on the left, what makes this statement false? Well, we know our main operator is this. I know my left side is this and my right side is this. Well, it's wherever this is false and this is false. So wherever my left side is false wherever my left side is false here and my right side is false here. Same rule applies. It just looks a little bit different because the statement that we're operating on is a little bit more complex than just a simple two-letter statement. So that's the wedge. Let's move on to the next one. Now let's do the conditional. So we'll do the same thing as we've done on the previous slides. We'll start with the arrow Q. Remember, left side is true, right side is false. You're going to get tired of me saying it. I'm going to say it every time that I write it on this screen. So what makes an arrow true? Thinking back to the slides before, what makes an arrow true is wherever the left side is false or the right side is true. So it's an or statement. It's wherever the left side is false or the right side is true. So we break it up in that way. We split the branches because we just said it was an or. We put the left side over here, put the right side, or sorry, I keep on screwing that up. We take the left side, which is here, and we put it on the left side that we broke off the branch there. And then we take the right side, put it over here. Remember, true is on the left, false is on the right. False is on the right, true is on the left. So that's how we break this one up. Now we take the same sentence, same statement, put it on the right side. True is, or sorry, false is on the right, true is on the left. So where is this statement false? Where is P arrow Q false? And remember from previously, it's false where P is true and Q is false. So both of those have to, both those conditions have to be met for it to be a false statement. Left side is true and the right side is false. That's the only instance in which it is false. So both of them stack on the line. Stacking meaning that we don't break the line up to branch it out. And that's how we write the conditional whenever it's on the right side of the branch. The left side of the conditional will go on the left side of the tree. The right side of the conditional will stay on the right side of the tree. Same no matter what. Keeping with how we've been doing this, let's do a little bit more complex looking sentence, but we'll find out that it works out the same exact way. So let's say we have P and, oh, sorry, let's not do and, let's do the conditional thing. Let's do conditional. Let's make this thing look pretty interesting. So I'm gonna use these two. Drop our line here. Use these two just to get rid of it. So remember, true is on the left, false is on the right. So now, same thing as we did before. Want to find the main operator. What's outside of all the parentheses? Well, it's the conditional. It's the arrow. Once we start moving inwards, then we see that there are more and more operators. But the one that's exercising on the whole statement, meaning that we have a left side and we have a right side, is the arrow. So we're going to use the arrow rules when we're breaking this one apart. So what makes an arrow true? Because it's on the left side of the tree here. So what makes it true is wherever the left side is false or the right side is true. I probably should have given myself a little. This will work out. So we see the right side goes over here and we're marking it as true. And we have our left side, we're marking it as false. So same thing as we did with just the P arrow Q, this just looks a little bit more complicated. Once we start moving beyond this branch, we would look at what the main operator is here. We could technically drop these parentheses because they're just really not doing anything for us anyway at that point. They would see, oh, I've got a wedge. And then just to follow this like we did on the previous slide, well, if we have a wedge, then we can say, well, what makes a wedge true? Actually, I screwed that up because I'm going to need some room. What makes a wedge true is wherever either one is true, either side. So we have side, we side. So Q, M, and T. And then we can even do this one because we know the rules for the ampersand. When is an M and T true? Wherever M and T are both true. So right there, that's just how we do the rules that we already have. But what we're focusing on here is just the arrow for the time being. So I'm not too worried about you knowing how to do this just yet. But just know that what we're doing is we're identifying the main operator, which is the conditional arrow here, and we break it up doing the same exact thing as we did before. We took the left side, took this left side, put it over here. We said it was false. We took this right side, we said it was true. Because if you remember the truth rules from the previous slide, what makes a conditional true is wherever the left side is false or the right side is true. And just for good measure, let's do this where it's the opposite way around. I might forget this exactly, but we already do. Say we got our line here, but our P arrow, Q, R, M, and T. So same thing as before, but now it's on the right side. So we're saying, what makes this a false statement? Well, our main operator is still the same. It's still our arrow. So what makes it a false statement is wherever the left side is true and the right side is false. Make sure I said that right. And again, we can drop those parentheses. We don't need them technically. We can have them there. If it helps you out for right now, you can keep them there. It doesn't matter. Those parentheses are implied to be there even if they aren't there. So either or, doesn't really matter. But we'll hold off on that for right now. But all we've done is taken our left side. We've said it's true. Taken our right side, and we've said it's false. That's what we're doing with these truth trees. So, same rules apply as in the basic P arrow Q sense, just it looks a little bit more complicated here. And I won't go through breaking this one up more, but we'll do that on the next couple slides. But I just want to be able to show you that the rule is always the same. No matter what the statement looks like, we identify the main operator. We identify if it has a left side or a right side. The only times that won't happen is if a tilde is the main operator. And then we just split it up accordingly. We put the left side where the left side goes, and we put the right side where the right side goes. And then we keep on repeating until we get to just the basic letters. But let's do the next rule before we get into all of that. The double arrow is our last operator. And so from here, or from this point, you'll have all the different rules and how to use them. And then you'll also be able to start doing the actual truth trees. We'll do a couple practice problems on here, and then in another lecture I'll give you some practice problems, and then practice problems will be what we do for the next handful of weeks, like I've said before. But make sure that you always refer back to this presentation if you have any questions about how to apply the rules. Just keep on looking back at this if you're not sure exactly what you're doing, and then of course you can always email me if things are just not clicking. But again, once you do more practice problems, it should start to make more sense. If you hear me doing them and keep on staying diligent with this, then it shouldn't be too bad. But let's do the double arrow first. So we start as we had before. Let's just start with P double arrow Q. Anything on the left is true, anything on the right is false. So, what makes a double arrow true? What makes P double arrow Q true is wherever both of them match. So either both P and Q are true or both P and Q are false. So we will split our tree and we will say wherever P and Q are true, remember left side is true, so it's wherever both of them are true or both of them are false. So remember, the code word here is or. We hear or, we know that we're splitting, and then we're going to put whatever is on those sides of the or in their right spots. So P double arrow Q is true wherever both of them are true or both of them are false. Now, P double arrow Q, say it's on the right side. Remember that indicates that it's false. Anything on the left side is true. What makes P double arrow false? Well, what makes it false is wherever one of them is true and the other one is false, or vice versa. So this is also an or statement, so we will split our tree. So it's wherever the left side is true and the right side is false, or wherever the right side is true, or sorry, the left side is false and the right side is true. So you see both combinations there. You see where the P is true and the Q is false, or where the P is false and the Q is true. Both combinations. And so that is the double arrow rule. Whenever it's on the right side, you split the branches and you stack the two propositions, one on the left and one on the right. When it's on the left side, you stack them after you split the branches in two, and they both go on the same side. So here again, let's look at a more complicated view of the same thing that's going on here. And after this point, we will have all the rules. And what's nice about logic is the fact that that is all you need to know for the next 4 to 5 weeks, plus translations that we've already done. The translations aren't too bad. But if you can just get these 5 rules down and understand how a truth tree works, you already have the content for the next 4 weeks. I am not adding anything new for the next 4 weeks. It's just these 5 rules. So, let's just say we have tilde, P or Q, double arrow, tilde, just because it looks like I'm running a row, tilde T. So left side is true, right side is false. So, what makes a double arrow true? Well, first off, we should make sure we recognize that we have a double arrow that's our main operator. We have a right side and we have a left side. The double arrow is sort of demarcating those two different parts of the statement. So what makes this a true statement? What makes it a true statement is whenever both of these sides match. So either it's probably not going to be enough. Let me just go ahead and give myself a... So it's going to be wherever both sides match. Wherever tilde P or Q is true and tilde T is true. Or wherever tilde P Q is false and negated T is also false. So same thing as before. We take the left side and the right side, we split them apart, and then we branch it off and we stack them on the same side. Either both of them are true, so either both of them are true, or both of them are false. One or the other. That's what makes the double arrow a true statement. Now let's do the same thing. Take a little bit more erasing. That's all right. Again, see if I can statement I just used here. There we go. And that was too long to begin with. I should have known. All right. So we had tilde P or Q, double arrow, tilde T. So again, we recognize our main operator is this. We have a right side, we have a left side. So what makes a double arrow false? Because false is on the right, true on the left. Whatever makes it false, or what makes it false, is whenever they don't match. So wherever the left side is false and the right side is true, or the left side is true and the right side is false. So this is another or statement. Should do about that. Probably made a little bit too far. So wherever both sides are true, oh, sorry, take that back. Wherever they don't match, that's what it should be. So wherever they don't match, so left side is true, right side is false, or left side is false and right side is true. Sometimes these things can get a little messy, so it's always good to go back and double check, because as you just saw, I almost flubbed it up. So again, same thing applies as before. We take our left side, we make one of them true, we make one of them false. We make one of them false, we make the other one true. So whenever you encounter something on a truth tree, your first question should be, what's the main operator? Your next question should be, which side is it on? Is it on the true side or is it on the false side? And then after that, you should ask yourself, what's the rule when it's either, false or true, according to whichever side you find on the truth tree. And that will tell you exactly what to do, and you keep following that rule until you get to just all the letters by themselves, which you'll see here on the next couple slides. We'll do just a couple examples, and then I'm going to give you, like I said, another lecture of practice problems, and then we'll go back over those practice problems in another lecture. So how we're going to operate from here on out is I'm going to give you practice problems in one lecture, and then I want you to do those as sort of like a pseudo homework. You're not going to turn them in to me or anything like that, but if you want to practice them on your own outside of class time, that's what you should be doing. And then we'll go over them in the following presentation. So let's just do a couple easy practice problems to finish this lecture off. And then we'll move on to just doing pretty much practice problems for the next 3 to 4 weeks. 3 weeks, I think. So for our first practice problem, let's just start with this one here. So remember how we read these logical sequences is that we have our premises on the left side of our therefore sign. So this whole thing is one premise. This whole thing is our conclusion. And they might look a little scary at the beginning because we've just been doing pretty basic ones. But again, the idea is that we identify the main operator and then just use the rule. So even though things might look scary at points in this class, just remember it's just a step-by-step process. So what we do first in our step-by-step process, though, is we've got to list it on the tree. So remember that we have true on the left and false on the right. And what we want to do is we want to list our premises as true. Make sure that we write them down right, too. And we want to list our conclusions, or sorry, our one conclusion. There will only be one on the right-hand side as false. So that's our starting point right there. And again, if you want, you can draw a line, that's fine too. That little line is just saying, hey, this is what I was given at the very beginning. So now it doesn't matter which side we do first. We can do the premise first, we can do the conclusion first. It doesn't really matter. What matters is whether or not we can determine if it's valid or invalid at the very end. Let's just work on the premise here on the left side. And the first thing we do is we look for what the main operator is. Now we see that there's 4 different operators. We see that there's 2 tildes, an arrow, and an ampersand. And so we have to ask ourselves, what's the operator that's operating on the whole statement? Well, what's outside the parentheses? Well, we have this tilde here that's outside the parentheses. We have this arrow that's outside the parentheses. We have this tilde here outside the parentheses. Well, what's operating on everything? Well, it's this arrow. We have this as the left side, and we have this as a right side. Because the arrow is saying, if not P, then not Q and R. The tildes go with the 2 letters or the conjunction there on the right side, and just the P on the left side there. Those tildes are bound with those. But the arrow is joining those 2 statements together. So that's what we have here with the premise. So our main operator is our arrow. So what's the rule for an arrow? So with an arrow, it is true because it's on the left side. What makes it true is whenever either the left side is true, or sorry, wherever the left side is false and the right side is true. Now let's stick with what we're doing here. Let's stick with this premise. But let's just focus here on the left branch that we've built. We have a tilde P. What do we do with tildes? Well, we take them and we flip them across. So from this tilde P, we just write P. We flip the tilde across the line and remove the tilde. All right, so we've taken care of that. We've gotten down to the simplest thing, just the letter P. So now we need to get to the simplest thing over here. Well, what do we have again? Well, we have a tilde. So what do we do with a tilde? We just flip it across. We get rid of the tilde. I'm going to erase these parentheses just so it makes it a little bit easier. Now, we still have something else that we can do here, and that is Q and R is false in this instance. So what makes an ampersand false? Well, it's where either the left side is false or the right side is false. So we're going to branch again. Remember, either or. Either the left side is false or the right side is false. And we keep the letters on the right side because the right side is where the false is. So now we've taken care of this sentence. Now we just need to take care of this sentence. And what we're going to do when we break this sentence apart is we're going to break it apart on each one of our branches. On each one of our branch paths, we have to do whatever we do here on them. So, again, what is the main operator in this statement? Well, we have an ampersand here and a conditional here. The ampersand is within these parentheses, so that's conjoining those 2. But what's conjoining the whole statement is this arrow. So we have a right side and we have our left side. And now we have to ask ourselves, what makes an arrow false? Well, what makes an arrow false, thinking back to our rules, is wherever the left side is true and the right side is false. So what we're going to do is we're going to take the left side here, so this Q and R, and we're going to write it as Q and R as true on all of these branches on the left side, because we are breaking down that sentence. So wherever this arrow is or this arrow is false wherever the left side is true, or sorry, back up. This arrow is false wherever the left side is true and the right side is false. So it's an and, so we're going to put our P over here. And we're going to put our P over here. We're going to put our P over here. So let's go ahead and finish these out. We're going to have to stretch these lines just a little bit further. Hope that I've got enough room. Because the last thing we have to break apart is this Q and R. So what makes a Q and R true? What makes an ampersand true is wherever both sides of the ampersand are true. So Q and R, Q and R, Q and R. They all stack because it's an and. Because wherever this ampersand is true, is going to be, they're both going to stack. Both sides of them are going to be true. So now, before we start going back through and determining whether or not it's valid or invalid, I just want to show you that from this point on, they all look the same. They all look the same because what we were doing was we were breaking down our conclusion in all of these branches. We had to go and put them all in the branch below it, because when we break something down, we have to break it down in every branch that is still open, and we didn't close any of them off. So that's why you see the same thing in all of these spots on all of the branches, because you have to do the same thing on all the open branches that are down below. When you exercise your rules on something that's above, you have to break it down on all the branches down below. So just think of this first branch up here as the main trunk, and it filters down into all the other smaller branches down below. And so whatever you do on a main trunk, you have to do to all the other branches that you see. So now let's go back and determine whether or not the truth tree is valid or invalid. And remember, what we're doing to decide whether or not it's valid or invalid is we're looking for a counterexample. We're looking for an instance in which a letter appears on both the left side and the right side of our truth tree. Try to clean this up just a little bit. There we go. And let's start at the bottom of one of the branches and move up. So I see an R on the left side. I see a Q on the left side. I see a P on the right side. I see a P on the left side. Right there is my contradiction. I have a P on the right side and I have a P on the left side. That's our contradiction. If a letter appears on both sides of the line anywhere up a branch, then we can close it off. Let's go over here. I have an R on the left side. I have a Q on the left side. I have a P on the right side. I have a Q on the right side. I can close that off. I have a Q here and I have a Q here. That's a contradiction. I can close off that branch. Now let's look at the last branch. I have a R on the left side. I have a Q on the left side. I have a P on the right side. I have an R on the right side. I can close that one off because I have an R here. I have an R here. And remember that if you have a truth tree where you close off all the branches, that means it is valid. And that is all you need to do for that truth tree. You just have to say it's valid because you closed off all the branches below. I'm going to tell you right now that the next practice problem we'll do will be invalid, so we'll have to find a counterexample. But I just want to go back through this and just go step by step in what I did. So first thing we did was we took the premise and we put it on the left side. We took the conclusion, put it on the right side. We started with our premise and we looked at the main operator, which was our arrow. We used our arrow rules here to write those two. we took these two from here and we got rid of their actually I'm not going to use green, I'm going to use whatever color blue this is. Then we flipped them across because they both had tildes. So that was pretty much done to this point, except for we still had this negated Q and R. And so what we did was we broke that apart. I'm going to use, let's just use this burgundy type color. I went too far. Then we did this. We broke them up. And then after that point, we looked at our conclusion because we had broken everything down in the premise as far as we could go. So then we looked at our conclusion after this point. So we stopped looking here. We started looking here. And then we saw that our main operator was an arrow. So we said left side is true, right side is false in all of these branches. And then we had to break down this Q and R, which we did here. So again, this might look a little bit complex and convoluted right now, but the more practice problems we do, the more it will make sense. But that's the step-by-step to what we did here. Let's do another practice problem to finish off this lecture to show you what an invalid example looks like. So let's conclude with this example, and I'm going to tell you off the bat it is invalid. I'm going to put it up here in the margin to give myself a little bit more when I write this out. So let's start with how we have always started. I guess I should say how we always start these things. So remember, true is on the left, false is on the right. So how many premises do we have? Well, we have two. We have this one and this one. We only have the one conclusion here, so what do? We list our premises here on the left. Got G and H, double arrow I, and just H by itself. Then we also have not G I. So again, we can start wherever we want. I traditionally just start with the premises from the first one and work my way down. So let's start there. What's our first premise? Our first premise is this guy. And what's the main operator? We have two. We have these two. Which one is operating on the full sentence? Well, this ampersand is just working on the G and H, but this double arrow is binding the G and H and the I together. So we have a left side here and a right side here, and we'll use our double arrow rules. So what's our double arrow rules? Whenever it's true, it's either both of them are true or both of them are false. So let's split our tree, and we're going on one side to list them both as true, both G and H and I, and on this side we're going to list them both as false, G and H and I. So remember, the truth rules for a double arrow is that they both match. Either they're both true or they're both false. So we split those two up. Is there anything else we need to do to what we just did on these branches? Well, yeah, we have a G and H. So what makes a G and H true? Well, it's true wherever both G and H are true. So all we just did, we broke this thing down into these two. Now, what makes it false, which we find over here? So what makes it false is if either G or H is false. It only has to be one or the other. Since it says it's or, then we just break them up like this. Remember, false goes on the right, true goes on the left. So this has turned into this and this. Now we've done as much as we can to this first premise. Done with this guy. Now we can move over to the next premise. Well, it's just an H, and we don't necessarily have to write them on both of the branches. It doesn't really matter. So we'll just keep that H up there, and when we track back through to look for a contradiction, we'll just know that it's on the left side. So now let's look at the conclusion. What is the main operator in our conclusion? Well, we have an ampersand and we have a tilde. What's operating on everything at once? Well, it's the tilde. The tilde is outside the parentheses and it's saying tilde G and H. So our tilde is our main operator. What do we do when the tilde is the main operator? Well, we just flip it across the axis. So we take our conclusion and we're going to put it on each of these branches. So we're going to flip it across. G and I. G and I. G and I. Sorry, these G's aren't looking as good as they can. Just repeat that. So we put the same thing in all three spots because that's what we're doing. We're using our rule on our conclusion, and we need to put them in each of the branches below that are still open. We haven't closed any off, so we just might as well go ahead and put them on each of the branches. Is there anything else we need to do? Well, yes, we need to break down this G and I. And the question is, what makes a G, or what makes a conjunction true? Well, it's wherever both of them are true. So we'll just list them both underneath, like so. And now we're done. We've taken everything to its smallest bits, meaning that we've taken it all the way down to its basic letters. There's nothing else for us to do. I'm actually going to give myself a little bit more, erase these eyes. It's these ones that are pretty low. There we go. We'll put X's or O's underneath of them. So now that we've broken everything up, we need to go back through and we need to look to see if there's any contradictions. So let's start with the furthest left one. I have an I on the left. I have a G on the left. I have an H on the left. I have a G on the left. I have an I on the left. I have an H on the left. None of those are going to cancel out. They're all on the left-hand side. So we mark it with a circle, meaning that it's open, and we know that there is at least one branch that's open, so we know it's going to be invalid, but let's go ahead and look at the other branches too. I have an I on the left, I have a G on the left, I have a G on the right. Oh, look, I have a pair that match. So I have a contradiction, which means this branch closes off. You don't actually have to circle the contradiction in a truth tree. The X will suffice, but I'm just trying to show you what's going on in these truth trees when we're doing this search for contradiction. So we can erase all this, and we know that it closes itself off. Let's look at the last one. I have an I on the left. I have a G on the left. I have an H on the right. I have an I on the right. Right there, I have that and that. And those close it off because that's a contradiction. I could have also, say I didn't come to this one just yet, or at least I didn't notice it. I could have also seen that I have an H on the right and an H on the left. That also builds a contradiction because I have an H on the left somewhere above and I have an H on the right that is further down on the branch, so I can close that one off. So I have contradictions in those two branches. I'm going to erase some of this to clean it up a little bit to make it look prettier. Get rid of all this. And now we go back through and determine whether or not it's valid or invalid. And we do that by looking at our branches and seeing whether or not there's any open ones. Well, I do have an open branch, this one in particular. These other ones are closed off, so can't do anything there. They're not telling me if it's valid or invalid, it's just saying that those close off. But I do have one open one. So if there is any open branch, it is automatically invalid. Any open branch will do. Doesn't matter if you have more closed branches than open branches. One open branch says this is invalid. So now that we found out that's invalid, we need to do our counterexample. And to do our counterexample, we're just going to go back through the truth tree. We're going to identify every letter that we have in there. So we have a G, an H, and an I. So I need values for G, H, and I. Values mean I need to know whether or not they're true or false. So let's look at that branch. I have an I on the left. That's true. I have a G on the left. That's true. I have an H on the left. That is true. So my counterexample to what makes this invalid is where every single one of them are true. And then that's it. You only do a counterexample for an invalid truth tree. And by figuring out their values, you just go through the open branch. You identify each of the letters present in the sequence. And then you give whether or not it's on the left side or the right side. If it's on the left side, it means that it's true. If it's on the right side, it means that it's false. So, again, don't be afraid if this looks a little scary. This is something probably completely different than what you've ever done in your life in school. That's fine. We're going to spend the next 3 weeks doing nothing but practice problems on these before the exam. So, you will receive no more content for the next 3 weeks. It's everything that you see in this presentation will be what we do for the next 3 weeks. All we're going to do from here on out, or at least for the next, until the first exam, is practice problems doing this stuff. So whenever you feel like you don't understand what's going on, look back through this presentation, because this is going to be sort of the keystone of the next, of this first half of the class, or this first part of the class. Go through it. Make sure you've got some notes. Make sure you got the rules. You need to make sure that you have the rules. None of this will make sense unless you have the rules to the truth trees, and it's going to be helpful if you just have the rules that I presented earlier in the presentation too, where it just said what makes this true, what makes this false, because the and or statements will help you remember what you're doing. And you stack, ors you branch off. You'll hear me say that through all these other practice problems that we'll do. Just like with saying true is on the left and false is on the right. It's always the same. So, again, don't feel too afraid. Don't feel overwhelmed yet. We're just going to do nothing but practice problems for the next few weeks. If you have any questions, you're always welcome to email me, and we can always go over more problems. So, until then,